Imagine a war where breaking the enemy's code could decide the fate of nations. During World War II, the Allies achieved one of the greatest intelligence victories in history by breaking the German Enigma code. That story is well known. What is far less known is that at the same time, the United States built a cipher machine so secure that no enemy ever broke it. Not during the war, not after the war. It protected the most sensitive American communications at the highest level. Presidential messages, strategic orders, decisions that shaped entire campaigns. And it was designed not by spies, not by generals, and not by codebreakers in the field, but by an engineer working quietly inside an American factory. His name was Joseph Desch. Joseph Raymond Desch was born in 1907 in the United States, in the state of Ohio. He grew up in a civilian, non-military environment. His family had no background in intelligence, cryptography, or the armed forces. His early life was shaped by American industrial culture rather than by academic or military institutions. Desch studied electrical engineering at the University of Michigan, one of the leading engineering schools in the United States at the time. His training focused on practical engineering disciplines, electromechanical systems, electrical control, timing mechanisms, and machine reliability. He was not educated as a mathematician or cryptographer, but as an engineer concerned with how complex systems behave under continuous use. After completing his studies, Desch joined National Cash Register, NCR, in Dayton, Ohio. NCR specialized in building electromechanical machines such as cash registers and accounting systems designed to operate continuously with minimal failure. These machines required extreme precision, strict quality control, and predictable behavior over long periods of operation. At NCR, Desch worked on complex electromechanical assemblies, where consistency and durability were critical. His responsibilities included system design, testing, and manufacturing oversight. He developed expertise in building machines that could be reproduced at scale without variation, and that maintained stable performance under stress. By the late 1930s, Desch had risen to become chief engineer at NCR. In this role, he oversaw technical design, production standards, and system integration. His work was not about innovation for its own sake, but about eliminating failure. A machine that worked most of the time was not acceptable. It had to work all the time. At the same moment, the United States was entering a period of rapid military and industrial expansion. Although the country was not yet fully engaged in the war, American planners were already studying the lessons coming from Europe. One conclusion stood out: modern war depended on long-distance communication. Unlike European powers, the United States faced a global communication problem. Commands had to travel across the Atlantic and the Pacific. Messages passed through radio links, cables, relay stations, and human operators. Each step increased the risk of interception or error. Encryption was no longer optional. It was strategic infrastructure. American encryption systems at the time relied heavily on procedures and operator discipline. Security depended on correct usage, secrecy, and human reliability. Experience overseas had shown how fragile this approach could be. When procedures failed, even advanced ciphers collapsed. The US military understood that copying foreign systems was not enough. The problem was not only cryptography, it was reliability. An encryption system had to work under stress, at scale, and without depending on perfect human behavior. This is where Joseph Desch's background became relevant. Desch was not known for cryptographic theory. He was known for building machines that behaved consistently. At NCR, failure was unacceptable. This mindset aligned directly with military needs. As communication security became a priority, the US Army and Navy began looking beyond traditional intelligence circles. They needed an industrial solution, a machine that could be manufactured, maintained, and operated reliably by thousands of people around the world. NCR drew attention for this reason, And within NCR, Joseph Desch was the engineer responsible for turning complex requirements into dependable machines. By the time the United States moved closer to open conflict, Desch was already positioned at the intersection of military necessity and industrial capability. He had not yet been given a classified mission, but the conditions that would lead to it were already in place. Communication security was becoming a problem that engineering alone could solve. By the time the United States entered World War II, communication security had become a critical vulnerability. American military operations depended on radio and cable networks spanning oceans and continents. Messages travelled through multiple relay points, often exposed to interception. Unlike Germany, the United States could not rely on a single theatre of war or a centralised command structure. Its communication system had to function globally, continuously, and without compromise. The US Army and Navy agreed on one point: existing cipher systems were insufficient. Many relied on procedural security, operator discipline, or predictable mechanical behaviour. These weaknesses had already been exposed in Europe. The United States needed a machine-based solution that removed human error from the core of encryption. This requirement led to a classified project involving the US Army Signal Corps, the Navy, and industrial partners. National Cash Register was selected not because of cryptographic expertise, but because of its ability to build complex electromechanical systems with extreme reliability. Within NCR, Joseph Desch was placed in charge of the engineering effort. The goal was not to improve existing cipher machines. It was to design a fundamentally different system. The machine that emerged from this effort became known as Sigaba, also designated ECM Mark II by the US military. Its design departed sharply from European cipher machines such as Enigma. Instead of relying on a fixed set of rotors driven in a predictable sequence, Sigaba introduced a layered control system that made its internal behaviour non-repeating and resistant to statistical analysis. At its core, Sigaba used multiple sets of rotors, each serving a different function. One set encrypted the message itself. A second set controlled how the encryption rotors advanced. A third set introduced additional variability. Crucially, the motion of the encryption rotors was not directly tied to keystrokes in a regular pattern. Instead, it was governed by internal electrical logic that changed continuously. This design eliminated the structural weaknesses that had made Enigma vulnerable. There was no simple stepping mechanism. There were no predictable cycles. The machine produced ciphertext, with no exploitable repetition over practical message lengths. From an engineering perspective, Sigaba was complex. From a cryptanalytic perspective, it was opaque. Joseph Desch's role was not to invent the cipher theory behind Sigaba, but to ensure that the machine could be built, operated, and maintained without introducing weaknesses. This required strict control over manufacturing tolerances, electrical timing, and mechanical synchronization. Any deviation could have created patterns. Any inconsistency could have undermined security. Desch imposed production standards far beyond normal commercial requirements. Components were tested repeatedly. Assemblies were inspected for minor variations. The goal was uniform behavior across all machines deployed worldwide. A cipher system was only as secure as its weakest unit. Unlike Enigma, Sigaba did not depend on secrecy of procedures. Even if an enemy obtained the machine, its internal complexity and lack of exploitable structure made cryptanalysis impractical with the technology of the time. This was a deliberate design choice. Security was embedded in the machine's architecture, not in how it was used. Sigaba was deployed at the highest levels of American command. It was used for communications between Washington and overseas commanders, and for secure exchanges between Allied leadership. It handled messages where compromise would have had strategic consequences. Importantly, Sigaba was never broken during the war. There is no historical evidence of successful enemy cryptanalysis against it. Post-war evaluations confirmed that its design resisted all known attack methods available during the 1940s. This success came at a cost. Sigaba was heavier, more complex, and more expensive than simpler cipher machines. It required trained operators and careful maintenance. But the United States accepted these trade-offs. Reliability and security were prioritized over convenience. Joseph Desch managed this balance as an engineer, not as a cryptographer. His focus remained on ensuring that the machine behaved exactly as designed, under all conditions. He treated encryption as a systems problem, not a theoretical one. By mid-war, Sigaba had become a cornerstone of American secure communication. While Allied codebreakers focused on penetrating enemy systems, American leadership communicated behind a barrier that remained intact. The success of Sigaba demonstrated a different approach to cryptographic security. Instead of relying on clever tricks or procedural secrecy, it relied on controlled complexity, redundancy, and engineering discipline. This approach reflected Desch's background. He did not seek elegance, he sought failure elimination. By the end of the war, Sigaba stood as the most secure cipher machine deployed by any major power. Its existence remained classified for decades. Its designer received no public recognition. But its impact was immediate and decisive. The United States had achieved something rare in wartime technology, a system that worked exactly as intended, under global conditions without compromise. Yet even this achievement was only part of a larger transformation. The principles behind Sigaba pointed toward a future where communication security would no longer depend on machines alone, but on a deeper understanding of information itself. That shift would come next. When World War II ended, Sigaba did not become a public success story. Unlike Enigma, it was not displayed, celebrated, or discussed in the press. The machine remained classified, and its existence was largely unknown outside a small circle of military and engineering personnel. There were practical reasons for this silence. Sigaba had been designed for a specific wartime context. It was large, heavy, expensive, and required trained operators. It was never intended for widespread tactical use or for civilian communication. Its role was strategic, not universal. Once the war ended, military communication priorities began to change. The immediate post-war period saw a rapid shift in technology. Electronics replaced electromechanics. Vacuum tubes and later transistors offered speed and flexibility that rotor-based machines could not match. Cipher systems began moving away from mechanical complexity toward electronic and mathematical solutions. As a result, Sigaba became obsolete, not because it was insecure, but because it belonged to an earlier technological generation. At the same time, the principles behind its design did not disappear. Sigaba had demonstrated that security could be achieved through architecture rather than secrecy. Its strength came from internal unpredictability, separation of control functions, and elimination of exploitable patterns. These ideas became foundational in later cryptographic systems, even as the hardware changed completely. After the war, cryptography increasingly merged with mathematics. Statistical analysis, probability theory, and later information theory began to dominate the field. Mechanical cipher machines were replaced by electronic systems whose security depended on mathematical properties rather than physical mechanisms. Joseph Desch did not transition into this new era as a public figure. He did not publish academic papers or promote his wartime work. Much of what he had done remained classified for decades. When Sigaba was finally declassified, the cryptographic world had already moved on. Desch returned to industrial work at NCR. His wartime role was never widely acknowledged during his lifetime. Unlike many figures associated with codebreaking, he did not become part of popular history. His contribution remained embedded in systems, not stories. From an engineering perspective, Sigaba's legacy is clear. It proved that encryption could be treated as a systems engineering problem. Security could be designed into a machine from the beginning, rather than added afterward. Reliability, consistency, and controlled complexity mattered as much as mathematical cleverness. These ideas influenced later military communication systems, even when their physical form changed. Secure communication became something that could be specified, tested, and certified, rather than trusted blindly. In this sense, Sigaba marked a transition point. Before the war, encryption often depended on secrecy of design and disciplined usage. After the war, security increasingly depended on formal analysis, architecture, and predictable behavior under attack. Sigaba stood at the boundary between these two eras. Joseph Desch's work did not shape the future through fame or theory, it shaped it through proof. His machine showed that it was possible to build a system that resisted all known attacks of its time, not by luck, but by design. By the early Cold War, cryptography had become inseparable from engineering and mathematics. Machines disappeared. Principles remained. Sigaba was no longer needed. But what it demonstrated could not be unlearned. The end of Sigaba did not mark the end of the problem it had been built to solve. It marked a transition. After World War II, communication systems expanded rapidly. Military networks grew larger. Civilian communication exploded. Telephone systems scaled nationally. Radio links crossed continents. Early computers began exchanging data. The challenge was no longer limited to protecting a few strategic messages. It was about managing information at scale. Mechanical cipher machines like Sigaba could not meet this new demand. Their strength came from physical complexity. Their weakness was speed and flexibility. As electronics advanced, cryptography moved away from hardware-driven secrecy toward mathematical control. This shift required a new way of thinking. During the war, engineers like Joseph Desch proved that security could be designed into systems through architecture, reliability, and controlled unpredictability. After the war, mathematicians and engineers took the next step. They asked whether information itself could be analyzed, measured, and bounded independently of machines. This is where cryptography began to merge with a broader scientific framework. Communication was no longer treated as a mechanical process. It became a statistical one. Messages were analyzed in terms of uncertainty, redundancy, and noise. Security was no longer about hiding mechanisms, but about understanding limits. In this new environment, the principles demonstrated by Sigaba remained relevant, even as the technology changed. The separation of control functions, the elimination of predictable patterns, and the idea that systems must remain secure even when their design is known all carried forward into modern cryptographic thinking. By the early Cold War, encryption systems were increasingly evaluated not by secrecy or tradition, but by provable properties. Could a system resist known attacks? Could it tolerate noise, interception, and partial compromise? Could failure modes be predicted instead of discovered by accident? These questions reshaped military and civilian communication alike. Secure satellite links, early data networks, and later digital communication protocols all inherited the same assumption. Security must be engineered, not assumed. Reliability must be quantified. Behavior under stress must be understood in advance. Joseph Desch did not participate publicly in this transformation. His work belonged to a classified industrial era, but the mindset he represented did not disappear. It became standard practice. Modern cryptography no longer relies on machines with rotors and relays. It relies on algorithms, keys, and mathematical proofs. Yet the underlying goal remains unchanged. Eliminate exploitable structure, control complexity, and design systems that fail predictably rather than catastrophically. In that sense, Sigaba was not an endpoint. It was a proof of concept. It demonstrated that secure communication was possible at scale, under real-world conditions, without relying on secrecy of design or perfect human behavior. That lesson became foundational. World War II forced the United States to confront a new reality. Victory depended not only on weapons, industry, or manpower, but on information that could be trusted, delivered, and protected. Engineers like Joseph Desch addressed that reality with machines. Later generations would address it with mathematics. The transition from Sigaba to modern cryptography was not a break, it was a continuation. The machines disappeared. The principles remained. And those principles still define how information is protected today.